All right, so like I was just saying, the problem here already has this feasible region graphed for you. So in the last section, we were graphing systems of inequalities and graphing a feasible region. That's what this is. This is like that's already done here. So this is the feasible region. Feasible means like possible, right? So basically, the idea is that all the points in this region are possibilities, possible x, y ordered pairs for the problem. And starting tomorrow, we'll have applied problems. So you'll have, some kind of an application where this function is like maybe it's a profit function and you want to maximize your profits, right? Or maybe it's a cost function, you want to minimize costs. Or maybe it's maybe you're in engineering and it's a friction and you want to minimize the friction. So it's something that you're trying to like maximize or minimize. And then the feasible region is like all of the x and y values that are possible in the given problem. And so you're bound by these those inequalities that gave you the feasible region, and they're like they're called constraints. So, for instance, maybe you're running a factory and you make two products, and like X could be like the first product, maybe it's doodads, and Y could be the second product, and maybe it's whatchamacallits. And so you can make doodads and whatchamacallits, but there's like limitations, right? Like you have so much machinery in the factory. So based on the machinery, you can only make so many of those two products. And if you make more of one, then that's less of the other because they both need the same machines. Or maybe there's like a shipping constraint, right? Like you only have so many trucks per week. And so you can only ship so many of doodads and whatchamacallits. And if you ship more whatchamacallits, that's less doodads. So like each of those things would be an inequality that relates the two variables, right? Like a limitation on the two of them together. We'll see that when we get a little, like again, tomorrow, when we're looking at applications, we'll be writing those inequalities from the problem, from the application. Um, it could be based on labor, it could be based on cost, like any of those constraints. Here, that's all done for us. We have this region based on those inequalities, and every single point in this region is possible. Okay, so you can make and ship and sell any number of doodads and whatchamacallits as long as they fit in this region. So like 4-4, for example, 4-4 would be right around there. And 4-4 is a possibility. It's in the feasible region, so I could make and sell 4 doodads and 4 whatchamacallits. It works. And if I did that, if I plug them into this function, I'd get 6 times 4 is 24, plus 4 is 28. My profit, if that's what Z is, would be $28 or whatever. That's the basic idea. All right, so one thing you need to understand about this is if you're trying to maximize or minimize, which is the goal on these, right? We're trying to maximum and minimum on these problems. Because everything is linear here, the max and min values of Z are going to occur at one of the corner points, okay? Because everything is linear. That's something, I'll talk more about this as we get into this. Like I'll try to explain why that is a little bit, but for now, just take my word for it. I could prove it, but I don't think that's the best thing to start out with. So basically, once you have a feasible region and you know the corners of it, because again, all these are linear constraints, right? Since everything is linear, including the objective function, z as a function of x and y, it's just like 6x plus 1y. It's a multiple of x plus a multiple of y. Because all of that is linear, the corner points are what we're interested in. So all we really need to do here is test the corner points. Those are our candidates for the max and min of z. And whichever one gives us the biggest answer is going to be the max, and whichever one gives us the smallest answer is going to be the min. So z equals 6x plus y here. And my 4 corner points are 1, 1, 2, 7, 5, 10, and 6, 3. And you might be able to tell sometimes which one's going to be the answer, but you should show this work anyway, because this like justifies that answer. It shows that we're 100% sure this is the max and this is the min. So all I need to do now is plug these into that objective function, x and y, right? 1 and 1. So that's going to give me 6 times 1 plus 1, right, which is 7. Again, I'm giving z here. This is z over here. So 6 times 2 is 12 plus 7, that's 19. Bless you. 6 times 5 is 30 plus 0. Oh, whoops. I'm sorry. Plus, that's a 10, isn't it? Not a 0. So 30 plus 10, that's 40. And then 6 times 6 is 36. But only 3 here. Plus 3 is 39. So it's almost the biggest, but not quite. The biggest is at the 510. And so here's what my answer should look like. I'm going to say that the maximum, z max I'll call it, z like a little subscript max, is 40. And I'm just going to say where it happens. I'm going to say at 510. Okay. Now in a word problem, obviously I would want to give like a word answer. Since this is pure algebra, I'm just saying what the max is and what xy ordered pair it occurs at. We were also asked for the min. So z min is 7, and that occurs at 1, 1. So these are my answers. Easy enough? Before I shut up about this one and look at another one with you guys and let you try it, I just want to point out something. Again, you can kind of see some of the answers coming. Like, first of all, z equals 6x plus y. Both of these are positive coefficients on x and y. So that means when x gets bigger, z gets bigger. When y gets bigger, z gets bigger, right? So that means if you're going like any of these directions from the origin, z is going to get bigger because x and y are only increasing. Does that make sense? Okay, so your max is going to have to occur at one of those points out there. And that also means that this has to be the minimum, right? Because we're not, from there, we're not going left at all and we're not going down at all. So this has to be the minimum at 1, 1. So we could know before we did any math that our minimum is going to happen at 1, 1. The other thing I want to point out is that these answers, they're really close for the max, right? 40 and 39. But I don't know, when you look at this, if you just know that as x gets bigger and as y gets bigger, z gets bigger, it might be tempting to think, oh, that's got to be where the max is, right? Because it's like, it's the furthest like up to the right. There is this point here, which is a little further right, but it's only one further right, right? Like x is only 1 bigger there, but the y up here is 7 bigger. So doesn't it seem like this one should like run away with it? Why is it that when this one's so much like more kind of like up to the right, why is it that this one is so close? It's 39 instead of 40. Because the x coefficient is 6 and the y coefficient is only 1. That's exactly right. So if you look at the coefficients on x and y, 6 to 1, that means a change in x is going to make a bigger difference. 6 times as big a difference as a change in y. And so what happens is when you go from 5 to 6, z gains 6. When you go from 10 down to 3, z loses 7 because y went down 7. So that's why it did more than make up for it. That's why like this is still the biggest. But if it only went down to like 6.5, if this point was at 6.5 instead of 6.3, then this would have been the greatest. Even though, again, the drop in y looks more substantial than the rise in x, it's because of that coefficient being so much bigger. Okay, if you don't fully get that, that's okay. Because again, you're going to test the points anyway. But just trying to give you some insight so you can kind of see the answer coming.